Okay, this is for Earth Science. I went over chapter 26.1 yesterday. We'll look at the key idea, key vocabulary, and then go and complete the end of the section questions, okay? Observing the solar system. When you look up and notice that the sun has moved from east to west over the course of a few hours, doesn't it seem as though Earth is standing still and the sun is moving across the sky? This perception that Earth is stationary was the basis of ancient Greek theories that prevailed for over 2,000 years. The movements of planets and stars. For thousands of years, the predominant model of the universe stated that Earth stood still at the center of the universe. Such a model of the universe is called geocentric, or Earth-centered model. As long as 6,000 years ago, astronomers were recording the movements of the stars. They noted that the stars appeared to move across the sky, but they did not move in relation to each other. To explain the apparent motions of the stars, early astronomers envisioned the stars as holes in a solid celestial sphere that surrounded Earth. Beyond the sphere, they imagined was a source of intense light that shone through the holes. They concluded that the stars moved around Earth as the sphere rotated. Early astronomers also noticed that the same constellations or groups of stars became visible at the same time every year. People in many different cultures noticed this phenomenon and used the changing constellation as a basis for a calendar. Not all points of light in the sky are fixed in constellations. A few seem to wander across the sky, changing position over the course of days, weeks, and months. These wandering points of light are planets, and early astronomers inferred correctly that planets are closer to Earth than the stars are. Early astronomers noticed that most of the time the planets moved eastward in front of the background of constellations. Periodically, however, the planets stopped moving eastward and moved westward for a few weeks, then resumed their eastward paths. This pattern of apparent backward motion is called retrograde motion. And here's a picture of retrograde motion. View from Earth. The planet Mars seems to go backward during its orbit. The effect is due to Earth catching up with and passing Mars. So this is Ptolemy's geocentric model. And the Greek astronomer Ptolemy, Ptolemy, lived in Egypt in the 2nd century A.D. Ptolemy was puzzled by retrograde motion, so he developed a system that allowed him to predict where planets would appear in the sky at a given moment. To make his predictions, he needed to account for retrograde motion. Ptolemy succeeded in developing the first model that could be used to predict the locations of the planets. He imagined the planets on small circular orbits called epicycles. The center of each small orbit moved around Earth on a large circular orbit called a different. Retrograde motion occurred when the planet moved along the part of the epicycle that an observer on Earth could see. Ptolemy's model didn't work perfectly. Observations didn't always correlate with what the model predicted. However, Ptolemy's model was used by astronomers until the 16th century. Let's see. Copernicus, the Polish astronomer, proposed the heliocentric or sun-centered model of the solar system. Copernicus suggested that Earth was a planet that is rotated, and the Earth and the other planets revolve around the sun. The heliocentric model is the basis for our modern understanding of the universe. Astronomers observe what appears to be retrograde motion because each planet orbits the sun counterclockwise at a different distance and at a different speed. For example, Earth moves faster in its orbit than Mars does. Whenever Earth overtakes and begins to pass Mars, Mars appears to move west or backward among the stars. The effect is similar to what you experience when the car you are riding in down the highway passes another car. Both cars are still moving forward, but the slower car appears to be moving backwards. After Earth has fully passed Mars, Mars' normal motion appears to resume. However, the planet never stopped revolving counterclockwise. So we have Tycho Brahe was a 16th century Danish nobleman and an observational astronomer. Like let me go back up, see how Copernicus, I should know that. Like Copernicus and Ptolemy, he studied the heavens without the aid of a telescope. Instead, he devised his own instruments to observe the moon, planet, and other celestial objects. Unlike other observers, Tycho Brahe and his assistants studied the movement of the moon and planets throughout their orbits, rather than just at certain points. These more complete observations led Tycho Brahe to identify a number of unexpected occurrences, particularly in Mars' orbit. His records were the most precise made before the invention of the telescope. Tycho Brahe died in 1601 before he was able to apply his data. His assistant, Johannes Kepler, however, built on his lifetime of work. Through analyzing his data, Kepler discovered the unexpected occurrences could be explained if the planet's orbits were elliptical rather than round. That discovery led him to develop 3 laws that have become the foundation of celestial mechanics. Kepler's first law of planetary motion states that the planets travel in elliptical orbits with the sun at one focus. Instead of having only a center, as a circle does, an ellipse has 2 foci, plural of focus, on opposite sides of its center. So let's look at this. So instead of a circle, it's kind of stretched out oval. Because the sun is at one focus of the ellipse, a planet's distance from the sun will change throughout its orbit. Kepler's second law of planetary motion, known as the equal area law, states that each planet moves around the sun in such a way that an imaginary line joining the planet to the sun sweeps over equal across space in equal periods of time. Because the planet's orbit is an ellipse with the sun at one focus, the equal area law means that the speed at which a planet travels around the sun is constant. So it's saying it doesn't change. Kepler determined that planets travel faster when they are closer to the sun, although he was not able to explain why. His third law of planetary motion is the harmonic law, which is the time it takes a planet to travel one orbit around the sun is its period. The third law of planetary motion states that the period p of a planet squared is equal to the cube of its mean distance. So there's a relationship between how long it takes to go around the sun based on how far away it is. So here's the formula here. It is used to find the distance between the sun and a planet if the time period is known, or to find the period if the mean distance is known. So let's look at this. Kepler's equal area law states that a line connecting Earth to the sun will pass over equal areas of space in equal time. Because Earth's orbit is elliptical, Earth moves faster when it is nearer to the sun. Okay? So over here, January and December seems very much closer, right? And then over here, it's further away. According to Kepler's third law, the farther a planet is from the sun, the longer its period of revolution. One reason is that its orbit is larger. Another is that it moves more slowly than planets closer to the sun. The average speed of Earth in its orbit is about 30 kilometers a second. Mercury, nearest to the sun, moves about 49 kilometers a second. Isaac Newton and the law of gravitation. Believing a force was required to keep the planets in motion around the sun, Kepler incorrectly connected that force with the sun and its rotation. Isaac Newton, an English scientist and mathematician, developed a very different explanation for what kept the planets in motion. Newton's contribution to modern science is enormous, building upon the work of his predecessors, including Kepler and Galileo. He discerned and articulated 3 laws of motion and the law of gravitation, which he showed mathematically to be a universal law. Newton's first law states that an object will move forever in a straight line at the same speed unless some external force changes its direction or speed. What keeps the planets orbiting the sun? Newton said was the force of gravity. The law of gravitation states that every mass exerts a force of attraction on every other mass, and the strength of that force is proportional to each of the masses and inversely proportional to the distance between them. If an object moving through space is in a path that will take it by the sun, then as the distance between the two decreases, the force due to gravitation will increase. Because the sun has a far greater mass, the motion of the object, not the sun, will change noticeably in response to the force of gravity, pulling the object into orbit around the sun. Similarly, the sun is more massive than the planets, so its force affects the planets more than the planet's gravitational forces affects the sun. The sun's gravitational pull deflects the planets from the straight line paths they would follow under Newton's first law of motion. It keeps them in that elliptical orbits around the sun. Kepler had realized in his second law of motion that the planets did not move with constant speed with the law of gravitation. Newton was able to explain why they do not. Newton's laws still explain most of the interactions we see between objects on Earth and elsewhere in the universe. So here's our section review. What is the main difference between geocentric and heliocentric models of the solar system? So if we go back into our chapter, we're going to see the heliocentric, and that was Copernicus's astronomer who proposed that it was a sun-centered model of the solar system. He suggested that Earth was a planet, that it rotated, and that the Earth and the other planets revolved around the sun. The heliocentric model is the basis for our modern understanding of the universe. Okay, and let's see. We're looking for that before that. Geocentric. Here we go. And this is an earlier model that says the Earth is the center of the universe, which we know now to not be true. Okay? So let's go back to our next question. How did Ptolemy account for retrograde motion in his model of the solar system? If you remember, we were talking about how it looks like the car behind us that we're passing is going backwards, but it's not going backwards. It's just going slower than how we are, because we are going faster. So let's go back and see if we can find his ideas up here. And where he talks about retrograde. Here we go. Retrograde motion occurred when the planet moved along the part of the epicycle that an observer on Earth could see. His model didn't work perfectly. Observations didn't always correlate with what the model predicted. However, they did use the model until the 16th century. So we're back to number 3. Explain how Copernicus's model contributed to modern understanding of the solar system. So, the Polish astronomer, okay, so he proposed the heliocentric, which said that the sun is the center with the planets orbiting around the sun. And this is now the heliocentric model is now the basis for a modern understanding of the universe. And then he explained retrograde, the misconception that a planet was moving backwards, instead that it was just moving at a slower speed. Then, for example, down here it says, after Earth has fully passed Mars, Mars' normal motion appears to resume. However, the planet never stopped revolving counterclockwise. Okay, critical thinking. Develop a model or draw a diagram to demonstrate why Mars appears to travel westward across the sky most of the time and eastward for a brief period of time. So if we go back, and you can look at this model here, and then you can also review this area here where it gives you the example about the car, and you can draw a model of that. Okay. Number 5, mathematics. According to Kepler's third law, the period of a planet can be determined if the mean distance, mean is the average distance from the sun, is known. Okay, so we know the distance, then we can talk about how long it's going to be going around the sun. So Earth's distance from the sun is, say, 1 astronomical unit, and its period is 1 year. Jupiter's mean distance from the sun is 5.2. Use Kepler's law to find Jupiter's period. Okay, so you would go back here and look at P2 equals D3. Okay, try to use this formula to figure it out. And just see what happens, if it makes sense. And then you can also Google it and see if you got it right or not. Okay, so this is it for this section. Tomorrow or the next day I'll have the next section done. I will read it, and then we'll go over the terms and the section review. Please keep working. I will post this video. It's probably best if you just subscribe to the YouTube, so you don't have to keep going to the Google Classroom to get the links, but it's up to you. Please do your work. I hope to see you soon. Take care of yourself, and I will talk to you soon. Bye.